So I'm using the recording instead because it seems that the streaming has a problem. 所以我刚才有试了一下，直接把它串流到 YouTube 上面，让它可以存在那边，好像有点问题，所以我现在改用录影的方式，那可能之后再上传上去看看情况。好如果这个也失败的话，那就没办法了，就是他可能就没有留一份录影就是了。好，那如果还是一样，就是如果分享荧幕有问题的话，请再让我知道。那可能没办法，就跟上礼拜一样了。Okay, so today the topic is autoencoder. So the first part we'll talk about the vanilla or the simple autoencoder itself, and which will include a homework. And then we are going to talk about the variational autoencoder, which will include more about the theoretical part. The distinction between the variational autoencoder and the autoencoder is kind of interesting to kind of illustrate the practical side or the theoretical side of what we should do for the generative models. And then we're going to talk about the VQVAE, which is also used in the modern models like diffusion model. So you will see that if you download a diffusion model, you will see a part called the VAE. The VAE is sometimes just an autoencoder, but it is a direct descent of the VQ VAE, although the VQ part is gone, which is a little bit complicated and has a history, but we'll talk about it later. And also, the diffusion model itself can be considered as a kind of autoencoder. To be precise, the denoise autoencoder. 好，所以 autoencoder 其实在现在的模型中也有用到很多，像是 diffusion model， 你下载的时候就看到 VAE， 那个就是从 variational autoencoder VAE 那边来的，但它比较像是从 VQ VAE 那边继承下来的，因为有 VQ gain， 一开始的 stable diffusion 那边 latent diffusion， 它从 VQ gain 那边过来的，但是它要把 VQ 拿掉了，那一地方留下来的一个 VAE， 所以 diffusion model 自己本身也可以看成是一个 denoise autoencoder， 所以 autoencoder 虽然看起来比较简单、比较古老，但是在很多地方都还看得到，而且它还算是现在还算是一个很常用、实用的技巧。And in addition to this autoencoder part, we will also kind of preview what a generative flow is, which is related to GAN and diffusion model. But we'll just go a very quick overview about it if we have time. And then maybe if we also have time, we'll go to some technique window shopping for go back to September last year and to do a very quick window shopping of the new models back then, if we have time. So now let's start it with the autoencoder. So you can see that we have a slides right here. So I will follow slides. First of all, one way to, although we have a textbook recommended in the course page, and I have recommended several books back then in last week, but there are many different ways to learn things. For some topics like autoencoder, which is quite major, and still but it is still relevant to modern technologies. One way to learn that is from the Wikipedia. Although, because this technique like autoencoder has developed for quite a long time, so reading a textbook is just fine and a pretty good way to learn it. However, because it is so fundamental and so basic, so one quick way to do that is to learn it from Wikipedia. A lot of topics has a pretty comprehensive description and succinct but comprehension discussion and descriptions in Wikipedia pages. For example, Autoencoder is one of them. So one way to learn that is from Wikipedia. And besides, Wikipedia also gives you some links to the resource or textbooks so that you can go further to study of them if you want to learn more. So the problem of choosing a textbook to learn it is because if you are really new to this topic, you probably don't know which textbooks you should read. And even if you follow the textbook, sometimes because the textbook including all the fundamental or basic things, so probably you are not be able to find the topic you are interested in unless you read the first quarter or maybe first half of the book. And because the book itself is self-contained most of the time, but the chapter about, say, autoencoder may not be maybe depend on the previous chapter. So that may make you a little bit harder if you only wish to understand the topics of autoencoder. So if you have more time and wish to investigate all fundamental ideas in an area, then the textbook is the right way to do that. Or maybe a lecture note for a more latest results. But if you just you already know some basic fundamentals, but you want to know certain like terminology or certain techniques, then Wikipedia is one way to do that. And it is easy to access, has reference like it says. And also, because you read from Wikipedia, you know that the fact is on the Wikipedia page. So every time you want to check result back, you remember something, but you didn't remember it precisely. You want to quote something, you can go back to Wikipedia on your phone or on your computer. That is very acceptable and easy, very convenient. I would say that. 好，所以 Wikipedia 有它的很多好处啊，就是你随时都可以取得它，而且你丢个连结，大家就可以连到它，而且是你不用担心有版权啊，因为它就是大家都可以取得，不用说哦，我这边我买了这本书，但是别人没办法看到，我要截图又不能截太多啊，那所以会有很多各式各样的问题啊。But there are also cons or drawbacks about learning from Wikipedia. It is a little bit boring if you are not really curious about this topic. If you are just sometimes the Wikipedia is not trying to writing the topics in a more motivative or more funny ways to do that. If you are writing a book, you probably will want to write it in a more interesting way. But Wikipedia is more about information. If you still need to be motivated, then probably Wikipedia is not a good idea. Although sometimes it gives you some history background about how this topic is development. But sometimes it is a bit boring. And people consider reading Wikipedia is unprofessional. So if you are aiming to do a more formal or more research or academic way, sometimes you don't want to quote the Wikipedia, but you can always to go to the reference in the Wikipedia. Then these references are usually just a good source that you can quote it from. So okay, so the reason that I'm introducing this learning from Wikipedia is a lot of topics here are taken from Wikipedia pages. So if you see anything and you want to confirm or to check of them, you can go to the Wikipedia page. I mean, in the content in these slides, if you think, oh, I need some confirmation, I need some source, then you can go to Wikipedia and find of them. 好，所以这边我其实就是因为我们这边很多内容都是从 Wikipedia 拿出来的，所以这边稍微说明一下。Okay, so first of all, the definition. Like always, a terminology may have slightly different or maybe a significant different definition in different contexts. 好，所以定义这件事情很有趣的是，你在有的时候会在不同的书或者不同的领域不同的书上会有一些小小的变化，但是不同领域有可能它的定义上的差距会不一样。有的时候是方向上的问题，就是哪一个东西更基本你有两个性质 A 跟 B 两个性质 ，A 可以推到 B，B 也可以推到 A， 但有时候我们会选择 A 当做所谓的定义，有的时候会把 B 当成是定义。那有的时候甚至它不是 A， 只有 A 推到 B，B 不能推到 A， 但是在有些情况之下，就是有一些前提之下 ，B 可以推到 A， 那这时候有时候会拿 B 当做前提，当做定义啦，因为那个所谓的前提其实是一个好的条件，那有时候你不需要一个很糟糕的条件，所以很多时候定义会有一些差距。So because the definition may vary in different contexts or have slightly variation or maybe significant variations in different contexts. So when I give the definition here, is you know that it comes from the Wikipedia page. Okay, so we have two space. Actually, just two sets. Each space is just a set. 好，所以我们说一个空间，空间其实是一个比较弱的词啦，它代表说我们隐含中间可能会有一些结构或什么东西了。但基本上这边讲的就是两个 set， 两个集合而已。集合代表它，我们先不管它的结构。Okay, so one is the space of decoded message, or the original one we call X, and the other one is encoded message called Z. So we have two spaces. The autoencoder has an encoder and the decoder part. The encoder part maps from, so this encoder is a function to map X from the space X to the Z space. And the other is a function from Z back to X. So this is the definition. This is a definition of the decoder and the encoder and the decoder. Encoder and the decoder. Okay, so basically, just like maybe we talked about it before, at least in some class. Okay. In a lot of time, the definition may be overly generalized. 所以很多时候定义有点点太一般性或太抽象，它这边本身没有包含太多的性质，没有包含的它的性质。那它这边还有多了一句，就是 almost always one example is X is Rm, Z is Rn. Although it is not part of the definition. The definition is just, okay, we have two sets. One set is X, the other set is Z. And we have two functions. Actually, the function has a parameter. So it's kind of like a neural network or any machine learning models which has a parameter so that we can tune or train or to adjust it. So we call it a family of functions. So the encoder family, we denote it by the E and has a phi as parameter, which is just a family of functions that from X to Z. And the decoder is the Z to X. So actually you don't need to be too afraid or to be too nervous about it. Okay, so it seems too simple. I don't know how to derive any property of it. I don't know. It doesn't seem to be any useful. If you think about it, it kind of you're kind of Correct. You are right, because it is just saying the purpose of this definition is just give a name so that we can discuss it later. We use a more convenient name like encoder and decoder, so we are all on the same page. That's all. That's all. But because this one is just too abstract, so it actually gives you some concrete example. That is, okay, you don't need to think too much about, although X, I mean, in definition, we have to do that. Although X is in general, it's just a set. It can be a very complicated or very ugly set, but most of the time, it's just Rm, which is just the Euclidean space. And Z is also another Euclidean space with different dimension. That is Rn, with some m and n, maybe different, maybe the same. Most of the time, actually, the n is much smaller than m. It's significantly smaller than m. So it gives you a concrete case. So it is just a pattern of doing the definition. First of all, we're doing a very general, more abstract, and maybe not very useful definition. And we'll give you some concrete example, and when we add more properties when necessary. 所以这是一个标准的在科学上定义或偏向理科的其实资讯也是一样的定义的一个模式啊。一开始的定义都是过分的简单，那不用太担心，因为本来就是这么简单，他没有说很多，他这边的唯一的目的只是在告诉你说，以后我讲 encoder 的时候你就知道哦，它是从 x 到 z， 然后我讲 decoder 的时候就是从 z 到 x 的函数。好，那因为一开始比较简单嘛，所以它这边甚至这个 x 就是一般的任何一个 set 都可以定义，保留一个空间，就是未来我们在讲介绍的时候，你的有可能不是 Rn 空间，但现在其实它绝大多数的情况之下，它就是 Rm 跟 Rn 而已所以 Rm 就是你的欧式空间啦就是 R2 就是平面嘛 ，R1 就是一条直线 ，R2 就是平面那个坐标系统那个空间 ，R3 就是立体的空间，所以最后其实就会收敛到像这种情况，然后这个东西可能是神经网络啦，有没有具体上神经网络？但是它一开始定义的时候，只是要告诉你说x 是到 z， 然后 z 到 x， 它有一个空间在那边，然后这是一个函数对应过去。它这个函数，你看它只是说一个 family， 然后有 parameter， 那这 parameter 需不需要连续的，或者是可以微分的，可以做 gradient descent 的？它这边都没有说为什么不说？这边只是保留一个空间啦，但是之后大部分的情况之下，这边其实 Rn 嘛，然后这个 parameter 我们现在绝大多数都是用神经网络目前我们在课程或者是最近在做的事情，大家都神经网络，所以其实你这个东西就是神经网络你可以把它看成是一个神经网络，另外一个神经网络叫 decoder， 一组神经网络叫做 encoder 所以一组是因为它的 parameter 可以动了那不同的训练下面还可以动，所以你有一个神经网络是 encoder 那它是神经网络，因为它的参数可以调嘛，所以它是已经是一个 family 了那有一个 decoder。唯一的要求就只有 encoder 的输出可以当做 decoder 的输入。不过你事实上反过来依照这个定义 ，decoder 的输出也可以当做 encoder 的输入，所以他们是可以套在一起的，就这样子而已。Okay, so basically, if we kind of seeing the illustration right here, the encoder is just a neural network, and we have a output to be a code. The code is in the Z that we see before. Also, this is X and maps to a Z, and maps to an H, which is in the Z space. And by using a decoder, we get an X prime. So the X prime and X may not be the same. But in the context of training an autoencoder, our target is, I mean, our goal is to train an encoder and decoder so that no matter what the X is, the X prime is very close or maybe even better, the same as X. That is our primary goal or objective to train our model。所以这边的话就简单来说，刚才的事情就翻译成实体来说，就是这边有个 encoder，这边有一个 decoder，那 encoder 你反正有一个输入嘛，然后就有一个输出，进来的时候是 x， 输入是 h， 输出是 h， 然后这 h 再经过 decoder 跑出一个 x prime。x prime 跟 x 不是一样的东西，但是它在同一个空间嘛，所以它的 dimension 它的大小是一样的。那如果是要训练 autoencoder 的时候，我们训练的目标是希望 x 我们的 objective 是希望 x 会等于 x prime 或至少很接近 x prime。So maybe you will think about, okay, this is something easy. So why do we actually need this definition? The reason is, okay, there are some benefit because it helps you to think more, can generalize this idea to many different players. So you can, even if you can actually have a lot of different variations about the autoencoders almost automatically by free or by very cheap, with some very cheap modification. So it gives you a lot of different possibilities. So that's one way to think. If you only think, okay, if we define it just like a neural network, input and output, and just like this, the one drawback is what if we change this encoder to another model, like maybe a support vector machine, or maybe other different functions, maybe like neural ODE models, or like a transformers model or other models. So in this definition, it includes every possibility. The other reason is we can talk about this kind of things in more precise or accurate way. 所以为什么要用这么比较一般性的定义？有两个，一个是它更广泛，所以你更容易举一反三，知道更多的可能性。因为很多事情讲这个东西之后，然后你给你个例子，你大概就可以想象出来其他的可能性。那另外一个是它可以让你更精确的把东西描述出来。为什么我把东西切一块？因为这看起来是一个函数，那只是这个函数是用神经网络来替代的，那这也是个函数。那这两个东西有点像或者什么，但它在什么地方？就是在那个空间里头，所以我们可以把事情说得更精确，有这个原因。And anyhow, it is even if you do not buy the reasons that I gave you before, this is the fact that how this world works right now. So every text, almost every description and text or textbooks are writing. You can see a lot of writing is right in this way. A lot of paper is right in this way. So if you have to understand or read if you want to read and understand the papers or other textbook or results, I think familiar with this pattern or style is necessary. They actually have, even if you don't think that the reasons I give is a good reason, at least there are reasons. So there are reasons to do that, and at least some people prefer or like these kind of patterns. So it just introduced that you don't need to be too afraid of this kind of writing style, and don't need to be think about, okay, this definition is just too abstract. All I am saying is, yes, this definition is abstract, and don't need to worry about it. The actually useful properties are actually in the later. They will give it more like a neural network and giving something. For example, if it is not a neural network or something continuous, it cannot be trained by using like a gradient descent method. So from here, you cannot saying that, okay, by I mean, you cannot generalize to this kind of abstraction and saying that we want to train this using a gradient descent or a method or using ADAN or ANW. You cannot do that because it is not even continuous. We don't even know it is continuous. That's fine. The sole purpose is to give a framework and give them a language so that people can commute and give so can think about the things in certain framework like a function. And because we know a lot of different way to construct functions, so people can generalize this idea, not just using neural network or the non-machine learning models. We can generalize this idea to different kind of things. Okay, so it go back to talk about the layers definition again. Okay, so the actually formulation of autoencoder, basically the definition is only clear about the encoder decoder. So what is an autoencoder? Right now we are doing more concrete and more real examples. So let's now think about neural network right here. Okay, so we are from a space X to F. So this F is actually the Z space and the Z to X. So we have an encoder and a decoder. This is written in different notations. So you can consider this phi and this psi as a family of function. 好，所以这边用不同的符号来写。第一个不同的就是这边用 F 当做你的 code 或者 latent 的 space， 而不是 Z。好，那另外一个就是它的那个 function family， 有点不太一样，写法不太一样。好，但是这边的话呢，你还是可以把它想象成神经网络啊，但是这边还是比刚才更精确一点，但是还是没有那么精确。好，不一样的地方我等一下会说，它从那边到这边来差了什么地方。好，这边还是一组所谓的函数 family， 一组函数 family。So both of phi and psi are just a family of functions. They are not necessary to be kind of continuous in any way. But but by the definition of these encoder decoder things, we know that they can compensate to each other, because the output, I mean the range, actually the corange of this function, the encoder, is actually the range of this decoder, so they can compensate to each other. Also, this one is a composition. If you are not familiar with this notation, it simply says, okay, we apply this function first on X, then apply the decoder on the result of the encoder. 好，所以这边其实这个合成函数了，所以这意思就是我们先用 X 做 encoder， 然后再去做 decoder， 只是这个意思。那这个东西之所以一定可以用的原因，是因为我们前面的定义，所以前面定义其实说了，只是说这两个东西可以结合在一起，而且这个东西的输出会跟这个东西在同一个空间。That's all. So the definition ensure that these two functions can be composite to each other, and the result value is in the same space as X. However, the more abstract definition only says these two spaces are sets. But if you want to do things like subtraction or X subtract to this result and actually compute the norm, the square norm here, it need to have some structure on it so that we can do the arithmetics like subtraction, addition, or maybe constant multiplication, or maybe we need to compute the norm. 所以这空间在原本定义它只是集合嘛，但是这边的话我们一定会需要它能够做减法或者什么，或者是那个做弄，所以干脆就不管了，就直接把它看成是这边它就已经不假装了，前面还装得很抽象啊干什么的，只是说几乎所有情况我们看我们都是 RM 和 RN。 那这边讲了 RMN 包含了除了就是它坐标那个空间之外，还有就是我们一般讲的向量空间了。可以做向量加法减法，然后计算它们两个距离啊，或者算 norm。这边就不装了就直接把这个当做向量空间了。当然这个函数这边还不需要是一个，比如说线性变换或者神经网络或什么或者任何连续变换，因为它只是一组的函数，一个 family 的函数。但这边的话，我们至少会需要一个能够减法和算距离的。所以这边整体来说，你要是在做一般化的话，其实也不见得一定要做减法或者是 norm，它就是要能够算距离就好了。所以这边基本上就是我这边输出了一个东西，跟我原来的 x 它的距离，我们希望它尽量小。那这边取的是 argmin， 所以这边不见得一定要是可以做 gradient descent， 因为这是理论上取一个反正我就是跑遍所有的 encoder 和 decoder，所有配对我都通通试试看，可能无穷多个，但我通通试试看。理论上来说，我找到一组能够让这两个东西最小的，是从 x 到 f 整体来说，然后可以让它最小的，这就是我要找的这两个东西，一个 encoder，一个 decoder。Okay, so it has to be a vector space. I mean, at least it need to have to can do the subtraction and do a norm. But in fact, the convention here is just in the vector space. It actually means the distance. If you consider it to be a metric space, it doesn't has to be a vector space, but it has to be a it need to be metric space. A metric space means two elements in this space. We can compute the distance between them. Okay, so in the convention of metric space, in a vector space, this square norm is actually the distance between x and the output of this encoder and decoder when applied to x. So this is the distance between them. So the whole thing means that we're going to find a pair of encoder and decoder so that the output of we can call this the reconstructed x is as close as possible to the original x. So that's the formulation. Another way to do that is if we can further to make it more concrete, so that the encoder and the decoder to be a simple neural network. So in this formulation, you can see that x prime is the output of the encoder and the decoder. So when we apply encoder first and the decoder it back. So this is x prime, or call it the reconstructed x. So basically we want them to be as close as possible. But suppose the family we know is just a neural network, then we can actually apply to kind of expand the phi and the sign here, so that this one is a neural network, a family of neural network. Of course, the W and the B is its parameters, so we can have a freedom to choose different kind of W and the B. And W prime and B prime is the parameter of the decoder. And this sigma is the nonlinearity. You can see that we have the sigma prime and the sigma, but in fact, they are not they doesn't need to be a learnable parameter, a trainable parameter, because so why do we need a prime and the lead here doesn't have to have a prime? It's just because we have a freedom so that we can choose different activation or nonlinear function. That's all. But you can see that it pretty much says just, okay, suppose this encoder family is a simple neural network and the decoder family is a simple neural network. So the whole formula is not too difficult. We can write it in this form. So it is not too difficult. It's still in one line. It's still in one line. And maybe you can do something about it. So that's the home formula of autoencoder. If the encoder and the decoder are simple, like the simple neural network layer. Also, this one is really simple because you can see that it's in fact just a neural network with 0 hidden layer. So it is we only have one. The encoder itself is a neural network with 0 hidden layer, and the decoder is also a neural network with 0 hidden layer. It kind of like linear regression with one nonlinear nonlinearity applied to a linear like a. It is a fine transformation because we have a bias right here, but it is so simple. 所以你可以把它看成是一个神经网络，但这神经网络是零层，它连 hidden layer 都没有，所以是有点退化的神经网络。你如果单看 encoder 是这样子，然后单看 decoder， 因为它只是 W 多少加 B， 所以基本上就是一个 affine transformation 加上一个非线性层。你可能放 sigmoid 啊，可能放 ReLU， 都可以啦，但是它原本可能是放一个 sigmoid 之类的东西，然后所以两个这个非线性层可能长得不一样，但是里面只有一个 WX 加 B， 就只有一层线性层而已。整体来看，就是 encoder 跟 decoder 加在一起来看的时候，就会是一个简单的一层 hidden layer 的神经网络。所以你可以把它完整的看的话，它算是一个神经网络 ，encoder 加上 decoder， 因为它可以倒在一起，所以它变成一个神经网络。然后它只有一个 hidden layer， 这里为什么这边写 H 的原因？这边中间是 code， 把它看成是 hidden layer， 只不过它输入的 dimension 和输出的 dimension 是一模一样。So if we put them together, because the encoder is a 0 hidden layer, a neural network with 0 hidden layer, with no hidden layer. And the output, I mean, the decoder is also. So if we compensate them to each other, the encoder plus the decoder can be viewed in a whole, can be viewed as a very simple neural network with one hidden layer, So this is input, and then this is output, and one hidden layer here. That is why we write H as here, because if we view this as a neural network, it is the hidden layer. We only have one hidden layer. This is input and output. The only thing that special or different to the general simple neural network. When I say simple neural network here, I mean a neural network with one hidden layer. So the simple neural network has input layer, and you apply a linear and transform. Actually, the affine transform and apply the nonlinearity. You got the hidden layer, and you apply the linear. I mean the affine transform on the hidden layer, and then apply maybe apply a nonlinearity. You got the output. That is the simple neural network. So the difference between the autoencoder and the general simple neural network is that the output layer should have the same dimension as the input dimension. So another way to define the autoencoder as the original, I mean the simple autoencoder, is a simple neural network so that the input dimension is the same as the output dimension. 所以如果我们现在只在这个下面来看的话，你另外一个方法来看什么叫做 autoencoder， 简单来说就是一个简单的神经网络，一个它的 input dimension 跟 output dimension 是一模一样的神经网络一个简单神经网络。那这边就是这种形式的，或者是说刚才看到这个形式的那个对，应该说到这边这个形式的 autoencoder 它其实就是一个整体来看，它就是一个简单的神经网络。那它的 input 跟 output 的 dimension 是一样的，我们把它就称为是 autoencoder，所以它是一种简单的神经网络。你可以这样看了如果用这个形式来看的话。So, but of course, if we replace the neural network or maybe replace the simple neural network to a more complicated neural network, so we get that is a very straightforward generalization. So sometimes, I mean, in many different ways, we also call them the autoencoder. But in a more more strict form or original form, it may look like a simple neural network, but I mean, and the input dimension and the output dimension are the same. Also, there are some history about the autoencoder. It first proposed as a nonlinear generalization of the principal component analysis, that is a PCA. So the only difference is that the PCA is kind of like an autoencoder. I mean, in a more general definition here, the PCA is also an autoencoder. But the only difference is that the PCA, every component is linear. Also, it is linear. There is no nonlinearity, and most of the time there is no BE right here. So it has a linear transform as the encoder and a linear transform as a decoder. Then no nonlinearity at all. So, but it requires to have a more like orthogonal properties on the and extra more requirement. Like you need to have the first principal factor as the output, the first output, and the second principal factor as the second output. It has more requirement, but it is an autoencoder, and the encoder and the decoder are both linear. And it does satisfy the formulation if you sort of reduce the dimension in the latent space, in the code space. It actually satisfies this condition. So it can minimize the output and the reconstructed vector and the input can minimize them. 所以 PCA 基本上你可以放在这个框架下面，只是这个东西是线性的，这个东西也是线性的。它有很多条件但其中一个它符合的性质就是，如果你把它中间的一些维度丢掉，那它可以确保说，这东西的确是最小的。当你这边是线性，这边是线性的时候，它是最小，但是它还有更多条件了，还有更多条件。Okay, so the history also says that the autoencoder also in the early days it has different names like auto associator and diagonal networks. I think people doesn't familiar with these names. I don't even remember these names until I see it again. Of course, I have read this before, but I actually have forget them totally until I read it right now. So it can trace back to early 1990s, because it comes from the PCA. So originally it applied to the dimensionality reduction at the feature learning sense. But the concept can be also used as a generative model of data, which we'll talk more about it later. And also, that is exactly why we talk about it, because it is one of the earliest generative models that have been developed. And it is simple. Some of the most powerful AIs in the last decades are involved autoencoders stacked inside deep neural networks. So in an early development of deep learning, people are struggling to train like deep neural networks. So there are a lot of different tricks to train a very like a neural network with 5 layers or 8 layers. So one tricks to do that is we do the pre-training, kind of like the large language model will do the pre-training things, sort of similar in spirit. But this is used to solve a different problem. That is, it is difficult to train very deep neural networks back then. So one way to do that is we train each different part of the model separately and put them together. So one technique is to train each part of the models by using the way of autoencoder. So we got a pre-trained weight, and then we stack this layer together. Because the input and output have the same dimension, kind of like a ratio network. The input and output has to have the same dimension, so they can easy. So one benefit is they can easily to stack together multiple times. So this is kind of in a similar idea that because autoencoder, the input and output has the same dimension. So you can imagine that we can do it, kind of stack them in multiple times. So we can have a really deep neural network. So that's one way to train it. And similar method like use the Boltzmann machine. Because it can also be trained in a like a unsupervised way or self-supervised way. So as you can see that here, because this is the things we want to train. This is the thing we want to train. And we only have X here. So we can train it without a Y with a label data. So we can consider the training of autoencoder to be using a unsupervised or self-supervised manner to do so. So we can collect a lot of different data without labeling. Because if we want to label the data, we need humans to do that, which is expensive and slow. If we can collect a lot of different data, a lot of data without labels, we can still train the autoencoder. So that's one of the benefits of autoencoder. We can use a lot of data and train them without any human labels. 好，所以早期会用，我们会来训练 autoencoder，其实有一个好处是它是 unsupervised 因为它不需要标记资料就跟 Boltzmann machine 也一样 ，Boltzmann machine 也是一个生成模型它也可以做生成的restrict Boltzmann machine RBM RBM 也是把它叠在一起，你可以个别训练，然后把它叠在一起。那这边也是一样，你可以把它叠在一起。因为它个别来说的话，它都是一个，第一个它都是生成模，你可以把它看成某种意义上是一个生成模型至少在某些意义上都可以看成生成模型波兹曼训当然就是生成模型了。这边 autoencoder 你可以把它看成是生成模型，然后你都可以把它各自训练，而且是 unsupervised， 然后叠在一起。Another similarity is to the modern large language model training, because large language models are trained usually also trained in a more self-supervised way. You don't need to be labeled. The data doesn't need to be labeled. I mean, they are training on text data using. If you are doing the birth way, you are doing the mask. This can be done automatically without human being used to do the label like, okay, this is a noun, this is a verb. You don't do that because we simply randomly mask the some part of the sentence and ask the model to actually complete to reconstruct the text. So or maybe like the ChatGPT way, like doing the the GPT way. So it do the prediction like auto-regressive, which we'll talk about in next week. But anyway, it's the similarity to the large language model training is it is not kind of self-supervised or like unsupervised manner to do that, and they are sort of at least in some sense they are generating models, and also kind of like diffusion models, very similar to diffusion model because diffusion models are sort of like a denoise autoencoder. So they are also in autoencoder, kind of autoencoder, and they are static in a different way because they are mostly shared weight. We just give it a parameter so that it knows they are in a different step, but we are reuse this autoencoder. When we do a denoising process, we reuse this autoencoder, denoise autoencoder multiple times. That's one way to feel what the diffusion model do. So I'm just saying that here we have some similarity in different techniques. Okay, so why do we want to use autoencoder? So first of all, let me give you the name here. The auto means to itself. Sometimes we say auto, we are mostly think about automatic. 我们在讲 auto 的时候，常常讲会讲的是自动。但自动什么意思？自动是它自己就会动，不需要别人。所以 auto 其实它的意思是自己的意思。它其实自己。So like a automobile means a car, which means it can move by itself. So autoencoder means the output and input are the same. In mathematics, we have something like automorphism, which is like mapping. Morphism is kind of like a function of mapping. Automorphism is a mapping from a space to itself. Also, auto means itself. An autoencoder, so that's a characteristic of the autoencoder. You can change the neural net to other kind of different models. You can make the neural net to be complicated instead of just a simple model. But the auto part has to be kept. So the input and the output has to be the same space. So one interesting part, and people may sometimes they overlook or sometimes they think it is strange, is because isn't it just simply learn that a function f so that f of x is equal to x? Isn't it too simple? 好，所以有一个你可能会观察到，也许你不会观察到的部分是，我们现在学的这个 autoencoder，它其实有个很有趣的地方是，我们要学这个函数 f 嘛，然后这个 f 要做什么事情呢 ？f(x) 等于 x， 那这件事情会不会太简单了？我们为什么要学 f(x) 等于 x？So isn't it just too easy to learn? And of course, I know the answer. I can actually have a linear function f to satisfy your need. The identity matrix. Also, if I'm using let me write here. Okay, maybe it's difficult. So one solution to this f is simply a matrix. So suppose we consider this R3 to this R3. Okay. We want fx to be x. The solution is a matrix, a linear transformation. 1, 1, 1, 0, 0, 0, 0, 0, 0. The identity matrix, which we usually denote it by I. So isn't it just the solution right here? Yeah. In fact, it is a solution. If you consider all the linear function, This ensure that Ix is equal to X. So that's all. That's all. So we can find the X here. So isn't it just too simple or too easy? The key point is we are not just finding F, we are finding a pair of encoder and decoder. And this encoder to decoder, to make this problem, I mean, we are almost everywhere. When we train a model, we are training this model to solve a non-trivial problem. This fx to x can be very trivial if we're not given the restriction to this function family, the family function. So we must have certain restriction on this family of functions. The key restriction here is, okay, so if you consider x to recall this graph here, prime, we have this one before. The key point is the dimension here. Let's call this the F space. This is Rn. We simply write it as Rn. This is Rm. To make this problem difficult, we will have to have n is smaller, is less than m. So this one is crucial. If n is equal to m or even bigger than m, larger than m, the problem is too easy. Sometimes it is still usable, which we will see, like we can have different restriction, like in VQ, VAE. But if you consider linear family, your n has to be less than m. So if they are linear and n is, suppose otherwise n is greater or equal to m, this problem is too trivial because identity matrix is a solution. If you add some nonlinearity to there, it is a little bit more complicated. But the general idea is, even if you have the nonlinearity layer, if n is greater or equal to m, or sometimes it is as in the same order as m, the problem is just too simple. You are not learning anything. If you want to learn something, most of the time you need this one, and sometimes you need this one to be rather smaller than m to make it useful. 好，所以它的关键点在于我们要有一些限制。那这个限制最常见就是中间的 dimension 必须那个 n 必须要比 m 要小，有的时候甚至要小很多。你用线性来看的话，线性就是刚才讲的 identity 就已经是解答了。那你如果让它的那个 n， 那当然因为你现在两个东西来会让它有解答很多，它不一定是 identity， 但是它是一个无聊的问题，它学出来的东西也不会有意义。那如果你加上那个一些 nonlinearity 进去了，就像是我们前面讲的简单的那个 autoencoder， 那当然有点不太一样，跟 linear 会有点不太一样，但是差不多大部分的情况之下，它还是太容易学了，因为你中间的那个资讯过多，神经网络其实学的还蛮会学东西的，所以中间的资讯会过多，你其实那个学不到太好的东西，因为那问题太简单了，所以大部分情况之下 n 要比 m 小，而且可能要小蛮多的。Sometimes, even if your n is much smaller than m, but because we are usually consider x as a subset of Rm, 因为我们常常考虑的 x 只是一个子集应该是反过来，子集在它的 Rm 的子集，所以有的时候即使你的那个 n 比 m 小，它还是会变成一个无聊或太过简单的问题。So sometimes even if your n are kind of small or significantly smaller than m, significantly less than m, because most of the time our x is a subset of Rm, so even if your n, sometimes even if your n is significantly less than m, it will still be a kind of trivial or uninteresting or too easy problem to solve. So for example, when we consider x to be an image, or say we have an image. Let me do it again. So suppose we have an image like let me put it like 1000 by 1000 resolution. So suppose this is an image of 1000 by 1000. If you want to run an autoencoder, it's kind of like to a dimension here, an output to a dimension right here. You want this image to be similar. Oh, this is x prime. This is x. You want the output to be similar to be the original one. So what should be a dimension of this n? So if you consider the dimension here at 1 million, because 1000 times 1000 is 1 million. So it is kind of like a subspace of 1 million. Your m is a million. So suppose your n is something like 500 or like 500,000. Only half of the that is, this is m equals to 1 million. Your n is like m over 2. Is this a good n? So I don't think so. If this is an image, then this is not a good n, because the problem is too easy. The reason is that most of the image, they are continuous. I mean, if you have a red right here, the neighbor pixels is probably have the same colors. 好，所以一个图片它的附近的点，通常都会，因为它图片的颜色都连续的，亮度都连续的，所以虽然它是一个 R100万的空间里头，你可以把它看成 R100万的子空间，但实际上它真正的 dimension 可能会更低。So because the continuity of the luminance or the color in each pixel to its neighbor, so the real dimension of this image that we are interested in is much less than 1 million. So for example, if we can simply resize, you can consider that we can simply resize it to be like 500 to be 500 and resize it back to 1000 by 1000. Even we do this kind of naive things, because the resolution is high enough. So if we downsample it and upsample it, they probably will look pretty similar. Although it may get a little bit blurred, but they will look pretty much similar. Sometimes if you are training an autoencoder and doesn't train well, probably you will get a worse result than what we do here by resizing it to 500 by 500 and upsample it back. 好，所以我们可以做个简单的事情，比方说我把它缩小成一半，500乘500，然后再回来，这都是 linear 的，缩小一半回来，然后再放大。你用什么方法放大都可以，可以用 linear 的方法去把它放大。那出来的图跟原来的图其实 x prime 跟 x 其实不会差太多。那有时候你不会训练那个 autoencoder， 你就训练一个 autoencoder 在那边啦。好，所以有的时候你训练一个 autoencoder， 中间是比如说是50万，好，是50万这边，我把手机先关掉。好，其实可以不用了啊。好，像这种50万，有时候你训练不好的时候，它是因为你这个50万其实比这个500乘500还要大很多嘛。500乘500大概是25万嘛，是25万，你这边是50万，比它还多。可是有时候你训练不好，你 autoencoder 中间你的 n 是50万，你有时候乱训练， 没有让它熟练，没有跑好，你甚至跑起来还原的样子，还比我直接把它当 size 啊500×500，然后再 upscale 回来还要糟糕。这就是很明显，这种东西是不行的。甚至有的时候你这个 n 甚至比那个 m 还大都有可能。哦，我现在讲的是单色的，我现在不管它 RGB，所以这边是为了让事情简化，但 RGB 的话也是类似的状况。好，那这边来说的话，你看，有的时候你甚至 n 跟这个一样大，因为我们在做那个 convolution 的时候，有的时候你会圈容会变多啊，干什么的。你现在圈容只有一个，然后有时候准备做好，很常见没有做好的话，中间的这个 n 其实超大，甚至比 m 还大。我这边还客气的让它是 m 的一半，但是有的时候会训练出来很烂的东西。假如你没有真的训练对，那就是很明显没有训练好。因为有一个很简单的解答，就是你可以把它缩小一半再回来啊，当然不是很完美啦，但是它这个其实你把它当做一个标准。如果你这个东西你的 Autoencoder 出来的东西比这东西还更烂的话，那就是没有训练好嘛。啊，那就而且就是本来问题就不重要，问题就不对，因为太过简单。好，所以这个东西可以告诉你说，你可以这样去想，你把第一个想法就是你把它缩小再放大，它至少要有这种品质。那你这个东西 n 太大了，而且还没有这品质，你这个问题就有两个问题，这个就是 n 太大了，因为这个东西可以太容易训练了。假如这个品质你已经可以接受的话，那这个东西太容易训练了，问题太简单。第二就是你可能根本就完全没有训练好。好，那所以要多小呢？So what dimension should we use? So depends on the quality. I mean the acceptable reconstruction qualities you wish to have in this model. So one way is to have a simple baseline comparing to your autoencoder, like the downsampling and upsampling again. And this depends on your resolution, original resolution. So that's one way to compare this. And the other way is to compare with like other compression method like JPEG or PNG. So it gives you an idea, okay, how many information to what is the actual dimension about the information of this picture. Or you give you an idea. Like PNG, you can have a lossless compression. So you can almost, you can ensure that if you are using a PNG here to here, it is also considered as an autoencoder. JPEG is also, but the JPEG, if you are using JPEG, the X prime and the X are just close, are not the same. But for PNG format, or maybe some case for a GIF, but for PNG, it is a lossless compression. So one way to estimate the information content in this image is to see the size of PNG. What is your expectation of the compressed size of this image if it is used in PNG? So that is a way kind of to estimate the dimension. Okay, so here's just some suggestion of what the restriction you should give to autoencoder. Okay. Another property or characteristic about the autoencoder is that it doesn't need labeling. It is self-supervised, or like the name suggests, it is a mapping from itself. For something to itself. So that's another convenient way and easy benefit of this autoencoder. Okay, so another concept like we mentioned before is the PCA. If you're not familiar with PCA, you can check the Wikipedia also. But basically, let me give you some simple. I'm still going to give some simple description about what PCA is. So first of all, like we mentioned before, it is an autoencoder with a linear encoder and a linear decoder. But not every autoencoder with linear encoder and linear decoder is PCA. I'm just saying that PCA is a kind of autoencoder with linear encoder and linear decoder. But a linear encoder with a linear autoencoder is not necessarily PCA. 好，所以 PCA 一定是 PCA 是一种 autoencoder， 你可以看成是一种 autoencoder， 它有 linear 和的编码和 linear 的 decoder。但是它的它有额外的限制，所以不是每一个 autoencoder 有 linear encoder 和 linear decoder 的 autoencoder 都是 PCA。但是它可以看成是 PCA， 但是它有那个额外限制。So another restriction is that the components are ordered by their importances in certain formal definition. Let's some definition about the importances. So, but intuitively, let's consider this data. So this is a data on a plane. So it has 2 dimensions on 2 dimensions. So we wish to the PCA is another way to view PCA is that it is a linear transformation, linear transform to find another coordinate system. So originally we have a coordinate system like here, like x axis or the y axis, but we wish to find a better coordinate system, which is also linear and orthogonal. 所以另外一种方法来看 PCA 是，我们希望找到另外一个更好的坐标系统，更适合来描述这个资料。So let's see this data. Although the original coordinate system like x-axis and y-axis can pretty much represent all the information, but as we can see that one important axis for this data is the long axis right here. 好，所以你可以看到这边有一个特别的一个向量。这边可能你要看一下这个，我这边可能好像没有那个可以。这边其实是没有那个。好，没有雷射笔的样子啊，这比较糟糕一点点。OK， 但是你看到这边有一个比较特别的一个轴，是这个比较长的地方，它有点像个椭圆嘛，它比较长的这个轴在这个地方，然后一个比较短的轴在这个地方，你看出来有点像这样子。所以我们说的重要性其实就是变化最多的东西和变化最少的东西。So the reason is that 所以最后我们要其实就是把它这个东西做一个旋转了，把这个东西当做 x 轴，这个短的东西当做 y 轴。那如果我们要丢掉一个的时候，我们会丢掉短的。So the transformation of PCA is basically we choose the most important one, like the longest one here, as the new x-axis, and the second one, because we only have 2, this is 2-dimensional sense. The second one as the second axis. So if you want to discard one axis, which axis should you discard? You should discard the short one. If you want to make sure that every data to keep the most information, then you should discard the shortest one. So if we want to measure the things that we kept by the norm of each element, like then if we discuss this axis, we can keep the most of the length of them. 所以它几个想法，基本上就是如果我们要丢掉一个轴的时候，我们要丢掉哪一个轴才最能够保留最多的资料？所谓保留最多资料，就是我现在每一个资料它其实都有一个长度嘛，某种意义上它可以看成长度。那我要丢掉一个轴，那希望它整体的长度还是长度，其实长度平方还是留下最多的话，我要丢掉哪个轴？那这边看起来就丢掉这个短的轴，因为它会变压扁了嘛。如果你是丢掉长的这个轴，它会全部压在这个地方，扁在这个地方，那所有东西都缩小到这个地方。 那看起来丢掉的东西比较多。那所以你被迫要丢掉一个的时候，你应该会丢掉这个短的。So another example is that I have a keyboard right here, small keyboard right here. You can see that here. If you want to discard one, at least it's a three-dimensional thing. If you want to discard one axis, which axis you want to discard? Maybe this one, the most thin part dimension here. If you want to discard two dimensions, probably the shortest two dimensions. I mean, this one you can barely see the depth of it, and so you just give something like this one. This is a projection, and you still get something. If you discard this guy, you get something like this one, right? You got the short edge and the depth here. If you discard this one, you get like this one, because when you see a camera, you have to camera is a two-dimension thing. You will just have to discuss certain dimension. So you want to discuss most. You want to keep most of the things. You want to discuss the least significant dimension. So the least significant dimension is this dimension. So if you discard that, you still got everything, almost kind of everything. 好，所以你如果要丢掉一个维度，因为我们这边刚好，如果看到我镜头这边的话，刚好是一个3D 到2D 的一个转换嘛。那所以3D 到2D 你要丢掉一个 dimension。那以这个键盘来看的话，你要丢掉哪个 dimension？ 如果你是丢掉这个最长的这一边的话，你剩下的就只有现在几乎看不到嘛，因为它有一个特别小。那如果你要丢掉是第2长的这个，你其实会好一点点，但是还是很小。那如果你是丢到最小的话，你其实看到的是现在看到这个是还是一个还不错的长方形，好，可以看到蛮多的东西。那当然你有不同的地方可以丢，比方说我只要转任何一个地方，它都会丢掉一个 dimension。但是丢掉最少东西的，其实就是你现在看到直接看到它这个地方。那这边刚好是因为比较长方立体的，应该说是立方体，比较容易看出来。但是一般的资料也可以做这件事情，你可以选择，如果你 PCA 它的做法其实是选择一个就丢掉，如果有 N 个，你要丢掉 N 减一个，只留一个，那你要选哪一个留下来？那以这边来说的话，它就是最长的这个东西是留下来。但是一般的像是 PCA 上面可以看到荧幕上面 PCA 这边的资料的话，它其实这个东西是可以算的啊，所以它最重要的那个就是留下来保留最多，每个东西都有长度嘛，所以留下来长度总和最多的哦，其实是平方啦，哦，所以它基本上平方来算的话就是 variation。So the PCA, the principal component, the first principal component is the axis. So consider like in Rn, we have an n-dimensional space. You want to pick one direction to be your first axis. And suppose you discard the rest of the dimensions. Rest axis. You just only keep one dimension. The one dimensions that remains the most information or most length, the square of length of the data. Then there's one direction. Or there are some mathematical property to ensure there's a maximum. Because this is the terminology is a compact sphere. If you are in a three-dimensional space or like a high-dimensional sphere, because it is compact and continuous, so you must have one direction and at least one dimension that keeps the most length of the data. So that's a PCA. And after you pick the one, then we can pick the second important one and the third important one, and so on. Then so we can order the different component to have different importances. And also a good thing about it is every component you picked will be orthogonal to each other。而且你这样挑的时候，你会刚好挑出来那个东西，刚好就是最重要一个，第二重要，第三重要，然后他们刚好都会互相垂直，然后变成了一个 so they will become an orthogonal coordinate system. Also, that's pretty much the whole story about the PCA definition. But if you want to actually compute it, there are some linear algebra things that help to do that. So, for example, for the first component, what we do is to find a transformation. You can see that the W here, actually, we are trying to find all the direction. You can see, you can read this formula. This argmax means we've tried to find all directions, and we do the projection, or like what we do the projection from 3-dimensional space to the camera. But here we only project to a dimension on the direction of W. We project this X on this W. So we actually do the inner product on all the data, and we compute the summation of all the square sum of the length。所以你这边其实就是你 X 跟 W 可能就两内积就是你做投影嘛，然后它的长度平方，我们把它通加在一起这边因为它这边是 norm， 所以它通通加在一起。So this is the sum of the all projected length, the square of the projected length. Then we check all the direction. We find the direction that keeps the most projected length. In other words, if we expand this formula in a matrix multiplication form, it will become something like this one. So this is a whole formula, and we can do some linear algebra things to find all the maximum argument maximum one. That is the best direction. And we can find the second most important one, the third most important one, and so on. 所以这边就是他真的去算的时候这样。那真正去做的时候，我们会用 SVD singular value decomposition 把这个 X 的资料去做 singular value decomposition. So, in fact, if we want to do it more numerical, stable, and more efficient way, we usually do the single value decomposition on the data, on the X. And because the transformation, if you compute all the principal value, suppose the T is the result of the decomposition of X into PCA, then we have T is equal to this guy. And so we know that our T is in fact U sigma, which is the U sigma here of the single value decomposition of X. Okay, so here is some result. I think it's MNIST. After we do the project the MNIST data to 2-dimensional. When we say 2-dimensional means because we call that PCA, we say that PCA is just a coordinate transformation. So when we try to kind of do the dimensional reduction, we mean that we discard all the unimportant dimensions. We only keep the topmost, like here is 2-dimension. We keep only 2 most important dimensions. That is the first principal component and the second principal component. 所以我们说它做 reduction 做降维的时候，其实是在做，就是我们刚才说，其实原本如果是 MNIST 有784个维度嘛，它其实你做 PCA 可以做到784到784可是我们说降成2维是什么？我们只挑最重要的前2个。那我们做挑前2个之后，我们等于是把784维压到这2维。So basically, we kind of squeeze the MNIST. We have 784 dimensions. We squeeze them into just 2 of them. And because we're using PCA, we're using the two most important ones. So you can see that in different category. I mean, in MNIST, we have 10 different category corresponding to the digits like 0, 1, 2, 3, 4, 5 to 9. So we use different color to represent different categories. If usually, if this dimensional reduction method is kind of good, we'll see that the same color points will cluster to some place. So if they are mixed up and doesn't see any pattern, then it is considered to be not so efficient, effective or not so good reduction. But if they are, you can see some pattern, or even better, they separate each category and isolate each category to different places, then we'll probably consider this dimension reduction is successful, because we only need to use these dimensions, these two dimensions, to do something like classification. It's enough to do classification, because suppose we don't have it right now because they are still kind of overlapped together, but suppose they are totally separated and isolated for each group, each category, then it is a very successful and efficient, effective reduction because we can use only these two dimensions to do the classification. 如果我们这个东西颜色分得很开，假设它全部都分开的话，那这是非常完美的 reduction， 因为我们只要用2个 dimension 就可以做，比如说 classification 这些问题。But now we don't have that. But still, you can see they are not simply mixed up together. They are sort of separated. We can see that like this is orange one, red one, and kind of a dark blue one, and pink one here. And this is light blue, something like yellowish things. So you can still see some pattern. But so this one PCA is sort of still pretty okay. I think it is fairly okay dimensional reduction. But our point is not exactly on the dimensional reduction. What we are saying is that we're comparing PCA to linear autoencoder. So this one is a autoencoder that's trained by using like the way that way to train an autoencoder. So you can see that they are similar in some sense because they look kind of similar, except that the dimension kind of like a rotated one, mirrored or rotated one, kind of mirror and rotated one. The reason is that the linear autoencoder doesn't have any constraint on the order of axes. So if we want to, there's nothing wrong to do. The constraint, the objective of the autoencoder does not prevent this reduction to be rotated or mirrored, because as long as it can be reconstructed back to the original form, they are considered the same. However, PCA has to be fixed, like the first component, principal component has to be the first axis, and the second one should be the second. So it has a fixed order of axis. It cannot be rotated or do like mirror, or might be able to do mirror, but it is able to do mirror, but it cannot be rotated because the first one is the most important one. The second one is the second most important. So that's the definition. And if you are following the the SVD things, they are actually fixed. There's only one solution here. So this comparison means that the linear autoencoder and the PCA are fundamentally different because the linear autoencoder can be sort of switch or x and y axis, or they can actually rotate it. As long as the linear space, the expanded linear space are the same. Because we can consider that because PCA is satisfy the optimization problem of the linear autoencoder. So it is the best solution. But the best solution is not unique. The unique is the space itself. It's not the axis. So any orthogonal coordinate system on this space is a solution. So you cannot. So it will be a kind of like a rotated PCA. But good thing is that they are actually look similar. 好，所以他们两个差异性在于它的因为 PCA 这个东西是一个那个 autoencoder 的那个解嘛，它的最佳化问题那个解，所以它空间差不多，除非它有多重解了，但大部分情况下可能就没有多重解，因为这是最好的东西嘛。那所以它这个东西就他们两个会很像，但是它没办法控制，它里头那个 autoencoder 的 objective 没有控制它的轴要怎么放，它只控制它。就因为解的问题，它空间要相同了，所以你会发现它是它一个旋转哦，它看起来会是它一个旋转的样子。而且常常我们训练的时候不会得到最佳解，因为 gradient descent 只会找到 local maxima 或 local minima 这种东西，所以有的时候也不见得就很像，但不会刚刚好哦。但是PCA 的任何一个旋转都会是它的最佳解。Okay, so another variation of doing the autoencoder is called, and probably more useful, is denoising autoencoder. So when we train the pre-train each layer, that we talk about, there's one historical use of the autoencoder is to do the pre-train for training a deep neural network. So one way to do that is train each of layer using a denoising autoencoder. And another denoising autoencoder we can see is that diffusion models. So each diffusion step can be considered as a denoising autoencoder. Okay, so what is denoising autoencoder? So sometimes learning f x equal to x is still too easy. Because sometimes because it is when you design architecture, it is difficult to limit the bottleneck bandwidth of the code. 好，所以有的时候是你这个你现在的那个你想要用一个可能 transformer 可能有什么东西的，它中间很难把它缩小，有的时候是这样子。And sometimes is that it is just the real dimension that we mentioned before is probably just too small. So it's very difficult to actually make this learning useful. But one trick to do that is we can add some noise to the input to make it the problem that we force the model to solve in the training phase to be more challenging. 好，所以我们有一个简单的做法，可以让我们在训练这个模型的时候，让它变得更有挑战性啊，你总是可以做。那就算是你本来那个 f(x) 等于 x 也还 OK，你其实都可以加这个。总之，它是一个工具，让你可以做的事情。怎么做呢？简单来说就是我们把它加上杂讯。So simply speaking, a denoise autoencoder as simply as this one. We get an initial input x, and we somehow corrupt it through some stochastic mapping. So this one is just meaning. Some of them people may read this kind of okay, this abstraction. I don't want to read this mathematical formula. 好，所以你看到这个有时候有点害怕，说啊，这个到底在搞什么？ But this one is just saying that okay, we are doing this process randomly. So when you see this tilde symbol or this operator, it means okay, this is some distribution, and we are doing this one. And QD basically means just is just a name. It is just a name. The name of this distribution, you must have a name. That's just like a variable name. And inside here is that by given x, we are trying to output a random output. So this, if I'm more like a coder, programmer, or like a programmatic thinking guys, this is just a random function process. The input is x and the output is x tilde. And the name of this function is qt. That's it. So although it has some scary name, like it is a stochastic mapping, okay, coming up with this mathematical formula. It's basically just saying, okay, let's do some random crop on this x and get x tilde. 好，所以这边其实基本上就是我们做某一些随机的破坏这个随机也可以固定的，因为有时候我们会是固定的破坏，但是就是做一些破坏那这个破坏可以是随机的。当你说随机的时候，你要知道完全不随机也是一种随机，就只是它的 distribution 就是每次都输出一样的东西而已，那它也是一种随机。你要是做一个骰子，它6面都是一样，你还是可以丢它，它还是可以，还是一个 stochastic， 只是它是一个无聊的分布而已。好，所以这基本上就是我们做一些破坏，而且这破坏可以让你有一个空间可以做随机的一些破坏。So how do we correct these things? Just like OS, this is a more generic or general description, more abstract definition. So to keep you have freedom to have a different method to correct or to add noise into X. So one way to do that is just add some like a Gaussian noise to it. But there are other ways to do that. Like you can actually mask out some content of it, or maybe just truncate it, like some part of it, or maybe both. 所以最简单的加法就是你直接加高斯，就是常态分布的高斯杂讯直接加进去嘛。那也有可能就是你把中间一块挖，如果是你想象这张图片的话，中间一块盖起来，那就是有点像是做 inpainting 那种感觉。也有可能是一个句子，你把后面一段去掉，就有点像是你在做那个 UPT 那样子，去做预测 autoregressive。所以它可以包含各式各样的去除，你甚至把整个 x 去掉，希望直接还原也可以，也包含在内，只是看起来意思并不是很好。好，但是它的名称 noise， 你一开始想的话，可能就是加高频 noise， 但是如果是以这个定义来说的话，你就是加任何东西，只要做一些事情让它跟原本不一样就可以了，可能把一些资讯让它不见就可以了。Okay, so we actually do the encoding, but instead of using x as input, of course, if we are using x as input, then everything should be the same. Instead of using x, we're using x tilde as input. But we still want the output to be as close as the original x. So this is called the denoise autoencoder. There are some ideas about the denoising autoencoder is that we wish the higher level representation are relatively stable and robust to the corruption of the input. So for example, if we are trying to do like a classification, like a dog or cat image classification, even though we add some noise on this image, we are adding some noise on this image. It probably doesn't change the fact that the category of this image. So if it is a dog and we add some noise on this image, it probably can still be recognized as a dog. This noise may be including like Gaussian noise, or some maybe we do the color tuning, change the color, or maybe we just, for example, we can do that. We make it a color image from a color image to a black white image. or maybe we simply mask out some part of the image. But if your goal is to do a classification, and we probably want all of these have similar representations because they are still dog. If all that matter is that we want to know whether this image is a dog or a cat, then a good idea is that no matter what noise is added on this image, the representation should be kind of stable. Doesn't change too much. When we say stable, we mean doesn't change too much. So we want the higher level representation. That is a code. So autoencoder is the major or principal. The primary use of the autoencoder is to kind of encoding it into a code. That code is a higher level representation of the input. So one assumption, one use case of a denoising autoencoder is that no matter what noise that we are adding in, we want the representation is relatively stable and robust against the corruption of the input. And also, if another assumption is that the question itself is more challenging. So to perform denoising well, the model needs to extract and knowing the structure or has more understanding of the input. So basically, if we're making the obstacle or the task more challenge, maybe we can train a better model. Also, that's kind of the assumption or the things we are hoping the denoising autoencoder can achieve. Okay, so there are some applications to the like a denoising autoencoder or like autoencoder itself. The one thing is dimensionality reduction, just like a PCA. But autoencoder can directly reduct to a lower dimension because autoencoder doesn't rate the importance of the access, but kind of like PCA, if we have a objective so that we can keep the most important dimensionalities, and because the model, I mean the encoder and the decoder are can be more complicated or more sophisticated than the linear transformation, so we can have a more powerful encoder and the decoder. Another way is because we like we say one of the primary usage is to find a code or representation, a higher level representation of the things, so we can do the information retrieval, sort of like the RAG you have heard for a large language model. It's always for retrieval, and we are all usually just doing things like we have information, a piece of information. We do the encoding, so we get a vector. So kind of like have a vector database. So for each piece of information, by finding the similarity of a query and the vector in this database, we can retrieve the information that is most similar to the query. 所以就像现在常做的 RAG 一样，它概念很类似，就是你要有一个 vector 嘛，然后我们才可以可能放到一个 vector DB， 然后去做你之后要 query 的时候，我们可以找到最相似、意义上最相似的东西，只是看什么编码而已。那这边 autoencoder 就是可以当做一个编码器，所以这是一种做法。事实上，如果你有一些，比方说你就是如果丢进去的东西就是用 VAE 丢了，可能比较少了啊，那些可能都是 clip 那些，或者一些VLM 那些东西弄。但是总之它概念上类似啊，就是你用一个 encoder 得到向量，然后我们可以去帮你做资讯的取得。Another usage is anomaly detection. So how do we do anomaly detection with autoencoder? One way to do that is we train on normal data, and maybe with noising it down, like using denoise autoencoder. So because we are training the autoencoder on the normal and the data with I mean the data without defect, so it will mostly reconstruct the things back to the original one, the normal one, because all the model has seen in the training phase is normal one. So to save the dimension, it will assume the input should be like a normal, especially if you have you are using the noise autoencoder. It will assume something that is not um, like its objective or target. It is something should be removed. 好，所以因为你在训练 autoencoder 的时候，你会把它压缩嘛，压到一个比较小的 dimension 再放回来，所以很多东西不必要。如果正常的东西都有的东西，它可能就不存了，因为每个东西都一样，所以它还原的时候会比较像正常的东西。So the reconstructed thing like x prime that we discussed before will be more like the normal thing. So the thing is, if you are putting a normal x in the encoder and decode it back, the output should be pretty similar to the original one. Even if you add some noise, if you are using a denoising autoencoder. But if you are putting a thing that with anomaly, like defects or kind of outliers to the models, it will probably doesn't perform that well. At least not like the original one, because you are actually overfitting. I mean, not exactly overfitting, like fit. You are fitting the model to the normal distribution. I mean, the standard, the distribution of the normal product or normal images or normal samples. 因为你就是在那个正常的样本上面训练的，所以你训练的东西，它就你的模型，特别是你要让它的那个中间的那个 code space 变小的时候，有一好就没两好嘛。它能够好好的把那个正常样本上面还原就已经不错了。所以你如果放一个不在正常样本里的东西，它可能就没办法还原好。那利用这种方式，我们就可以做 anomaly detection. So by comparing how well the reconstructed x prime is close to how close it is to the original one, the input one, we can estimate or by using as a metric measuring method to see whether it is a normal sample or an anomaly sample. Maybe it is a defect sample or maybe it's just an outlier. So that by using this method, we can do the anomaly detection. And sometimes we use this one to do because we are representing it in a different coordinate. So we can do it by doing image processing. There are many different ways to do that. In some of the machine learning thing, although it's, I mean, in recent modern models, we pretty much simply do some normalization to the input. That's all for pre-processing. But maybe like 10 years, 10 to 20 years ago, sometimes people does not send the image directly to the model. They do some pre-processing. Some of the pre-processing, including a zero component analysis, which will make the image to be more representative. So if you are doing something like a PCA or these zero component analysis things, the benefit is that you first of all you reduce the dimension. you reduce the dimension, actually, reduce the dimension. And you still keep the dimensions that is most different between the samples. 好，所以你的优点是你把那个 dimension 缩小了，然后而且你留下来那个 dimension，其实它的个别的差异是变很大。So the individual differences still can be sort of kept or in some sense emphasis because you reduce other dimensions. You only get a few dimensions. Because early days the model is difficult to train model, so we have to reduce the complexity of the problem itself to enable to do the model trainings like classification things. It is still similar today when we do like the audio, like speech recognition or like speech synthesis. People still do some like encoder or decoder things, like a vocoder. You may heard a thing called a vocoder, VOCODER. Because the audio or speech process we usually do some pre-processing to transform the things like male spectrum or do in there are other trained preprocessor to map these audios into another space. So we doesn't do the wave directly. Also, there are some models do the wave, the audio wave directly, like WaveNet. But there are other models, many other models, because the audio still have the frequency of model is quite high. So a lot of usual process is to do some pre-processing first and doing it on the list space. It's similar, kind of similar when we do a diffusion model or like a video, image or video diffusion model. We do the latent diffusion things. So first we use an encoder to encode things in a latent space. Then we do the things in a latent space. Then we transform or translate back from latent to the real representation, like the spatial color RGB space. Similar things still happens in diffusion models, in audio processing models. So that's the idea. And in fact, diffusion models are still using autoencoder. I mean, latent diffusion models are still using the autoencoder styles of things. You can still find the autoencoder in modern or current day diffusion models. 所以像 diffusion model 也是一样，或者很多的音讯处理也是一样，都会先做一个编码压进去之后，然后最后再让它还原。所以在很多地方都会这样做的。就当这个问题它还有点难的时候，可是像图片本身，图片辨认啊、辨识那个，后来大家都或者是什么像物件侦测啊那些，大部分都直接把图片就丢进去了。但是在很早期的时候，图片其实也会做类似的事情就是先做一个像是一些 transform PCA、ZCA 或者一些其他的，让它做一些处理之后再去做。那有时候会让它的那个东西提升，但是这些前处理有的时候会有点太会比较花时间了。那跟训练的时候会就如果你真的要用一个像是 ZCA， 它太大的东西不好弄所以 PCA 这种东西的话或者是那个 Autoencoder 这种东西的话 ，Autoencoder 还算好训练了但 PCA 的话，它也会像是 Autoencoder 那样子训练，就是它可以做一个，因为 PCA 如果你真的照前面那个矩阵分解，它有点太大了，所以它会做一些处理，让它可以处理比较大的资料但是如果是 Autoencoder 的问题就不大，因为反正就一个你就是你可以用 mini batch 这样子stochastic gradient descent 这种类似的方式去处理它。Here is some example. Although it is done by using diffusion model, not exactly using the autoencoder directly, you can use autoencoder directly. But it illustrates some of the things that we can do to do anomaly detection by using reconstructive based method like autoencoder. So suppose this is original image. You can see that there are some defect here because one of the foot is less, one of the leg is missing. But because the model or is kind of like an autoencoder, denotes autoencoder, and it has only seen the normal sample. So when it reconstructed, it actually reconstructed the leg back to the reconstructed images. This is because this is a diffusion model. Diffusion model can do a lot of amazing things. But if you are just using a simple vanilla autoencoder, we probably expected this thing to be some blur or strange thing right here. But diffusion model is so amazing, so we can see that it actually reconstructs the legs back here. We can compare the reconstructed image and the original input and see the differences. So we see the differences is mostly like here. So not only we know this one is kind of anomaly, and we can also pinpoint which part is the defect or the anomaly happens, which region is kind of anomaly. It's not normal right here. This here is another example, which is a little bit less of obvious, but you can still see here. It is not, if you know that this pattern here, you can see the irregular part is here, here, here. When you do a reconstruction, because like before, it is only trained on the normal samples, so it will kind of remove although this one is not become exactly the normal things, but it still, you can find the differences is quite significant and apparent. You can quickly find the apparent, quite obviously, these three parts are the regions that you may be interested in. And it actually corresponded to the part which has some defect. So that's the idea, illustrated idea of how we can apply the autoencoder to do anomaly or defect detection. Okay, so let's talk about the homework. Here we have some example code, like collab autoencoder using TensorFlow, but currently, probably you should use PyTorch because PyTorch is much more popular. I personally use PyTorch Lightning a lot to simplify a lot of process, but you just use it the PyTorch directly is a pretty good choice. Also, can you use, depends on your test, you can use either of them as your fundamental foundation to learn how to actually write a code of autoencoder. It's not too difficult. If you are confident in your PyTorch skill, you can simply write your own code. But here we present a few example code. I'm not going to details about how it should work, but basically every thing should, for PyTorch, the data pipeline should consider data set and the data loader. So it kind of look like this one. We have a training data set, testing data set, and we're using a data loader to actually construct a data loader. Data loader is kind of like a iterator. So in a training loop, you are iterated over the data loader. You don't need to use the data loader, but data loader provide. You can actually just use a list of things if you really want to do that, and you use it in loop because everything that can be iterated is fine. If you are using a PyTorch style of training, because a standard PyTorch style of training is just you have your own loop. So it is just a loop. You can loop anything that can be loopable, and it is your job to convert the samples to a torch tensor. But if that is more easier for you, I don't think that should be an issue. As long as you can write the data pipeline easily and to do whatever things you need the data pipeline to do. But I still strongly recommend that you are at least familiar with the data loader or data set. They are used so in many different places. The Lightning also has its own data pipeline thing, but I think using PyTorch, the data loader is just fine. The Hugging Face also has its dataset pipeline, but here we are not working on it. So you can use the Lightning code with PyTorch data pipeline, the PyTorch data pipeline, just like what I do. That is totally fine. But you can also use other choices like PyTorch model on your own training loop. Or maybe you want TensorFlow or Keras, that is still okay. And here is some example of how to write encoder and decoder for image data. So here is a standard convolutional network for encoder. The key idea is that we are using stride equal to 2 and without any pooling. So to make the model more simple, because you can actually write everything in convolution. That is called an all convolution network. But anyway, because we want to kind of shrink the dimension, the bottleneck dimension, the coding dimension. So we have to reduce the size of each of them. And at the end of this layer, it actually resize it into a linear thing. If you want to keep it in 2 dimensions, it's okay. But in this encoder, it actually resize, reshape it into everything into a latent dimension. So you can define your own latent dimension. But remember, latent dimension should not be too big. You can experiment several different choices, but the latent dimension cannot be too large. At least you should not larger than the original input size. This is a decoder. Because decoder has to kind of upsampling. You can use upsampling or other things, but the standard way of doing so is using convolution transpose 2D. The convolution transpose 2D can be considered as the inverse of the conversion. So if you are having the same setting of the convolution, then you will have a double size things. But there are some consideration about the padding and the output padding things. This is something you should understand by yourself. Because we are not teaching. I think this should be covered in the deep learning course. But I'm assuming you should have some understanding about what convolution transpose is. Otherwise, you will encounter some trouble if you want to define your own architectures. You will encounter like okay, you will report error like the dimension is not compatible or things like those other things. If you are so unfamiliar with convolution and it's just far beyond your understanding, you can use linear. I'm not right now. I'm not talking about homework. You can because I want you to have a basic understanding about the how to design a simple neural network. Otherwise, it will be getting difficult in the later part of the course. So, trying to design a simple model like an autoencoder here. Okay, so but here you need to understand what the convolution transpose 2D is. Even though suppose you are just it's just too difficult for you, you can use linear layers. That is still okay. But I strongly recommend you that to actually understand what the convolution and the 2D and the convolution transpose 2D is. And also there are another method is called the pixel shuffle. So if that is sounds familiar or sounds makes sense to you, you can also pixel shuffle. But anyway, the text is just writing the autoencoder. Okay, so here are two examples, just in case for your reference. So the autoencoder itself contains, if you are writing in the Lightning module, it contains encoder and the decoder model inside the Lightning module. The Lightning module itself is more like a configuration of the training. Although it is sort of like you can see that it is NN module. 所以你看到这个 decoder 这边有 NN module。NN module 比较像是一个模型就是 PyTorch 的 module。So the module in PyTorch is more like a model, sort of like model, although it's called module. It including how the weight, what is the weight here, and what is how we should actually use this weight to do the forward process. And the Lightning module, although it by name it looks like more fancy or advanced NN module, but in fact, it is actually a superclass of the NN module. That is for sure. But I think logically, it is more like a configuration of your training. So I think a good practice is still define your model by using NN module from PyTorch NN module. But you can define some properties like self-encoder to be a NN module and self-decoder to be an NN module, and use the other functions to sort of control the training process or like evaluation process. 所以 Lightning module 从名字上看起来好像就是强化版的 NN module，事实上你看 code 它也是继承了 NN module 没有错，但是在逻辑上我觉得它的比较像是它的意义上比较像是我在把那个训练的过程以及训练要做的事情把它绑在这个 module 里头。所以一个比较好的一个做法是把模型定义你还是放在 PyTorch 的 NN module 而且别人也可以用，但你在训练跟训练有关的东西，包含你训练的设定训练的 optimizer 训练的一些过程evaluation 需要的 metric 什么，你再放在这个里头这是比较好的一个做法。Okay, so this is a forward, although it is still kind of like the forward, like here, but the meaning is more like this forward is for the training. We are doing for training or for training process, like here, and so it has a configure optimizers and a training step. You define a training step, and you can actually call the trainer.fit to have a fancy progressive bar and to see a loss and maybe have TensorBoard integration, or maybe like weight and bias integration, depends on your logger. 好，所以它的优点就是在于你只要分别把这些 training step 定义好了，这个东西定义好了，你就丢到点 fit，然后给它这 loader 啊，它帮你处理剩下的事情，像是 logging 啊，你要 TensorBoard 或者 weight and bias 的 log，它有不同的 log，它有好几个不同的 log，哦，你可以换不同的 log，让它比较视觉化去追踪它。So even though if you are using your own loop to do the training, I will suggest that you still do similar things that the Lightning training loops do, like logging everything that is very useful information. Just log every information and save the checkpoint frequently, so that you can, if there are something wrong and something that is not successful as you would like or expected, you can always do the debugging and checking what is wrong. It's a benefit for production or benefit for actually learning the things. 好，所以你一定要加上很多的那个，所以你就算不用 Lightning 了，你自己写 loop 也要加上很多的资讯 log 和很多资讯。所以他选择其实就是在于哪一个对你来说比较容易做。有些人程式写得很好，那他就说反正我自己写，然后自由度又高。那 Lightning 的话，可以让你很方便的写几行，然后就弄完了。它有一个规定的一个标准，但是你有的时候会限制到你的自由度。如果你对它不是那么熟的时候，会限制到你的自由度。它还是有一些自由度上的限制。至少对我来说都还有限制啊。比方说，如果我要有好几个不同的 validation loader，当然也可以做到了，但是没有做到很优雅的方式去做。所以这是一些可能的一些问题，但是总之就是你要能够就是如果我真的要做一些很复杂，那我可能不见得一定会用它。但是就是这些东西是你的工具，然后如果你学会的话，你要用什么工具的重点是你有没有办法很快速把你想要的东西弄出来。那在这边的话，我们需要的东西就除了训练之外，你中间还要能够看到该看到的东西，然后你可以随时可以改掉你想要去改的东西。比方说，我想要改它的training 的 loss 啊，我换成别的 loss， 我要换成别的那个 schedule， 我要换成别的东西，你可以很快弄出来。Okay, so here is just some example of visualization that you can see in a TensorBoard. There are many different visualization methods that you can see, like reconstructed images or like the dimensional reduction to visualize how the every sample is placed in this latent space. Although you cannot see through the higher dimension space, but still by using a dimensional reduction, you can check is this latent actually working, or like what we did before, things like this one. Like this one. You can monitoring, is your model doing the things that is what you wish for or what you are expecting for. So if you are using autoencoder, we are expecting these things to be more separated and more, because especially if it is not, maybe you should change your like objective function, or maybe add more. Most of the time, it is something fundamentally wrong. I mean, your loss does not indicate the direction you wish the model to go for. 所以有的时候你发现这个不太对了，是你本质上你的问题就给错了。你给的 loss 是你希望一厢情愿，以为那个 loss 可以做到那些事情，但是不行啊。它有很多解法，它就是不能做到这件事情，因为你给的 loss 就是要把你的模型推到它要的东西，你不要给它任何选择。但是你有时候给的资讯不够，你只是觉得这个可以。那有的时候就是你单纯的程式写错了。So sometimes it's just simply you didn't write it, you have a bug in your code. So, but anyway, if you can see the process as soon as possible, if you cannot see it, you cannot defeat it. So if you can see it, you can kind of improve yourself and modify your code and get more experience. If you cannot see it, then nothing. It is very difficult to kind of improve your technique or coding skills or like the experience on this deep learning training. Okay, so let's talk about the homework right here at the last page. So this is our homework. So use autoencoder to generate the following data set for different latent dimension. 所以助教帮忙再把这个作业出到E3上面。So you are going to submit the homework on E3. Okay, so we have several different settings. This one should be considered like a warm-up sense. We don't have much restriction. We only consider the MNIST, and you try different latent to see how the latent dimension affect on the result of the training. 所以我们这边的主要实验是说，我把这个 latent 说，比如说 MNIST 的这个资料集，手写数字的资料集，它的真正 dimension 多少？64可以吗？32还是4？因为它的一开始进去的 dimension 是784嘛。So the original dimension is like 784, 28 by 28. But is 64 dimension is a good dimension or 32? So is it possible to reduce everything into like the 4-dimensional space? Is it even possible? How difficult is it to do this autoencoder training? And what is the quality of the final model you do? To be spoiled, if you want to reduce the dimension to be 4, chances are you are not going to get a very good results unless it is doable. It is possible to do that, but requires you to sort of modify or doing some certain ways to make the model to converge correctly or to a right direction. So if you are doing it first time, chances are it will output a result. The result output by the model is quite blur or maybe even unrecognizable. 所以4这个其实有点困难的，你要压到4，然后出来品质还不错，有点困难。64、32可能都还算简单，但4的话会比较困难。如果你压下去。And do this for facial MNIST. The difference between that is just build intuition about the content or variation of the content would affect to the model. So the model is how the model should be designed or how the latent space should be designed is depend on the model. I mean depends on the data set. Different data sets may require different settings. Like one of the important settings is the latent space, dimension of latent space. So it may require different space, different dimension. Okay. And also here we need some metric that you collect and some information you collect from the training or the resulting evaluation process. So one of is to calculate the mean square error and L1 error for training and the testing. I mean, when you train your model, you can use any loss function you like, any combination of L1, L2, or any like cross entropy or anything that they think is useful, and you can use also any optimizer. I'm writing this note is just because I'm asking you to measure the square error and L1 error for training and testing data. But I'm not saying that you should use you must use square error or L1 error when you train, or use any combination of them. I'm not saying that. I'm just saying that no matter what your loss function is, no matter what your objective is, I mean, in the standard definition, I mean, standard objective of the autoencoder is the square error. You can use that as well. But it doesn't mean you cannot observe the L1 error. Even though if you are training on the square error, mean square error, or like a L2 norm, it doesn't mean you cannot kind of monitoring L1 error. So all I'm saying is this text is ask you to monitoring or at least see checking. When you finally train, when your model is trained, we want to see, okay, what is the mean square error for the training data set? What comparing to the testing data set? Which one is better? Or the training should be better, but what is the differences? Is it overfitting or not? Or suppose, I mean, most of the time we probably use the mean square error as the objective function, the loss function. But there are different ways to measure how well it is constructed. Even though we are not using L1 as loss function, is the reconstruction can be considered good when we use when we measure it by using the L1 error。好，所以这边基本上就是说，反正你要用什么 loss function 是你可以决定，标准上是用 L2 了就是 mean square error 那是没问题的。那我这边只是说，因为有时候其实会碰到这种事情，不管是跟同学或者是有时候跟工程师也是一样就是因为我常会要求说，你会多观察一些东西 L1 或者是 mean square error， 常常会碰到一个一头雾水的反应，就是可是我用的 loss 是什么东西啊？这个不重要，重要的是不管是什么东西，你都可以去你在训练的时候，你用 mean square error 没有问题的但是我们中间还是想看一看，你用 P10R 怎么样子啊？你用 L1 是什么样子啊？因为它只是一种观察嘛，因为我们没有办法有单一标准看看我们还原的东西是不是好的当然以训练的标准来说，你用 mean square error， 那当然训练的结果就是 mean square error， 那是绝对的，在训练的有没有训练好用那个标准来判断。但是我们现在也许想要看的就是说，好，比方说其中有可能性就是因为我们没有用 L1 训练嘛，所以我们想看看说会不会是用mean square error 训练的时候，它同时 L1 也可以变得还不错的，而且我们没有特别对它去用这个东西训练，会不会它比较不会有 overfitting 的样子发生？就好像比方有人说音乐跟数学的相关性嘛，那可能你在练习的时候就是练很多音乐，可是可能会让你就补习或者是学的时候学了很多音乐，但是测验的时候可能测一下你数学，可能你数学的时候没有特别去做额外的训练或补习，但是会不会你在训练别的东西的时候，但是另外一个指标它会变好？这是有可能，或者你学数学的时候，物理变好了，测验物理的时候它顺便也变好了，或者你学物理的时候，因为你物理的时候更多应用嘛，说不定你的数学跟着变好，有点像这种感觉。Okay,所以第一个就是 so the first you should do the two actually the training 6 models for MNIST 3 for each of the data set MNIST and facial MNIST so that you can have a build up experience or feeling intuition about how the different data set affect the model performance just have building up intuition. And the first requirement is that calculate mean square error and L1 error for training and testing data. And in addition to the quantitation matrix, you also, in kind of the generative models, you also need to have some quality measure or metric or feeling about the sense. So showing 16 reconstructed image for 60 random images from training dataset and put it in a 4x4 grid. So this also asks you to have a way to combine to showing image in a grid. So originally this is designed to So if you does not have a experience or abilities to actually put in images in a 4x4 grid, so you can learn how to do that through coding. But right now, I think the primary goal is just I don't care. You can ask AI how to do if I have 16 images, how do I put them into a grid? Or you can just Google to find a utility function. Because PyTorch has or Lightning or a lot of place has a utility function to do the things. So for me, I can do it anytime using like a pillow or using NumPy to do that. That's is probably one way to do that too, but doesn't require to do that. I mean, all I need is if you are asking to provide this information, you can find a way by yourself to fulfill the requirement 啊，所以这边其实以前的话是可能是希望大家比较，因为特别有教到那个什么资料科学那个东西嘛，就可能难拍这个东西都可以做啊，或什么啊，但是现在可能比较，不过不管怎么样，就是你用什么方法都可以了，当然就是你问 AI 都可以，但是你要能够办法达成这个任务，也就是说，你可以第一个你可以看到你从reconstruct 的图片，而且你还可以把这个reconstruct 16个把它变成4×4的一个 grid。好，那当然这个也要 for。So of course you are doing the same thing again for a testing data set. And you can use okay, like my other course, you should do submit your homework in a single GP notebook to containing all the information that mentioned above. And you can use TensorFlow, Keras, or PyTorch Lightning, or other PyTorch-based frameworks. That is also fine. If you are using JAX or other framework, I think I'm okay with that. But I don't think I will encourage you to unless you have a very good reason. You should just stick with the TensorFlow or PyTorch, or mostly PyTorch. Okay, but if you really want to use JAX and have a really good reason, my attitude is that I don't care too much about it. The thing is just you have to do these autoencoders and do the comparison. That's the main point. It's just if you are using JAX, the teaching assistant might ask me, and it will get trouble. So unless you really need to use JAX or other framework, just use PyTorch or TensorFlow. 好，所以这边大概就是功课的一些，就是你基本上你就用 PyTorch，就因为大家现在都 PyTorch 啊，PyTorch 或者 Lightning，就是 PyTorch base 的一些 framework，你要用后面其实也 OK。但重点是我刚才讲的，这两个东西是要比较不同的 latent， 比较不同的 data set， 比较不同的 metric， 还有能够就是量化的东西，还有就是质化的这种你建立的感觉，就它出来的东西到底有差多少？还有就是像这样子的东西对应到的 L1、L2、L 大概长什么样子？这是建立的感觉，这是作业的主要的内容。好，我们时间好像差不多。我本来跟我预期的还是有点不太一样。我本来预期要在做那个variation autoencoder。哦，那这边的话，我先快速的带一下，它这边会很多数学，就是主要这边的重点之一是剧透是，我们刚才虽然说 autoencoder 是一个生成模型 ，so spoiler alert, although we call that we say that autoencoder can be as generative models, but if you really want to generate something, you will have a problem because this is also like a generative model, like a decoder. because we don't know what the Z space is. You say that I know what the Z space it is Rn, but we don't know the distribution on it because the X has a distribution. 所以你的输入 X 有个 distribution. So the distribution of X is mapping into the latent space. There will be another distribution in Rn, but the distribution of this inside this Rn, that is the range or the image. I mean the image. That is the terminology. We have function. We're mapping this distribution to map this into another space. It becomes a mapped or image of the distribution. 所以我们把原来的 x 这个输入映射到一个新的空间以后，它变成了一个新的 distribution. But the target distribution, we don't know what it is. So when we want to generate the image from the latent space, we do know what the decoder is. What we do not know is how should we sample the Z, because if we want to generate a new sample, we need to first generate the code or sometimes we write in H or maybe we write in Z right here. We need to know the distribution of this Z, but we don't know. So how do we do that? So one way to do that is use variational autoencoder instead, because after the training of variational autoencoder is very similar to training. Pretty much the loss function, only the loss function is slightly different. But it in the theory, it ensures that the latent space is a normal distribution. So we know what it is. So the variational autoencoder, in some sense, it solves the problem with that in autoencoder. If we want to use it as a generation model, we don't know the distribution of the latent. But in variational autoencoder, we enforce the latent. In training, we enforce the latent to be the normal distribution. But it is quite an interesting story behind the variational autoencoder. So I will have a dedicated hour to actually talk about it. We will go quite fast forward through the VQVAE and maybe a little bit generative flow next week. But right now, like last week, we can still have a very quick time to overview what can be achieved in modern day technologies and models, so that you can have a quick overview of what it is and what technologies exists today. So here is a note I correct, a slide I correct in last September. So first of all is the link fusion. The basic idea is it uses linear transform attention, like a linear transformer architecture instead of the transformer. 所以这边的第一个东西我快速介绍的东西是叫 link fusion， 这很常见的类似的东西，就是把那个 transformer 那一块换成 linear 因为 transformer 那个是 quadratic 的那个 attention 那些东西的2次以上的，所以很多要让它加速，然后其中很多就是 link， 看到 link 开头的大家都是在做这种事情所以它还是一样，只是把那些东西换成了 linear， 然后 and then it actually do the distillation from other models like stable diffusion models or like flux model or things like that. But it use a linear transformer architecture inspired by other things like Memba and other linear architectures. It actually still quite active. The good thing is the selling point is it is super fast. It says that one GPU, 1 minute, it can generate 16,000 images. So that is really, really fast. And it's still update at least until the December, November, a lot of updates. So this is a model that I didn't use it, but it seems to be quite still updating and quite interesting. And another is like a draw and audio, like video to audio synthesis. So it is also a form of an application of generative models. This is early. When I say early, I mean like 6 months ago. This is a song creator, like lyrics-based universal song generation. But currently, we have a lot of like music generated generative models. So this may not be the SOTA and may not be that interesting anymore. But still, this is one thing that exists that you can check about it. And this is another one, video to music generation things. This one is still relevant and interesting. It's called the Fine Video. This is a dataset by Hugging Face. So if you want to do some quick experiment and do some like video fine tuning of video model or things, or do some quick experiment on videos, Fine Video is a Hugging Face dataset that you can easily have access to it. So this is a dataset called Fine Video. And this is another image generative model. And this is a trainer for Flux, which I don't think is not relevant today because you can find a lot of different things. And this is, although you might not be that interested, but this one is a demonstration of how the generative model can be used in a more different way, alternative way to do that. This one is to do the material science to design some like a molecule or like other material things, but it uses generative models, including language model and diffusion model, to kind of generate new structure of the like materials。所以这是一个算是一个特别的应用了。它用了语言模型，也用了那个 diffusion model， 然后去生出新的一些结构，一些不同的结构出来。这是它生出来一些结构，一些材料的结构。这个可以当然这个问题不见得是大家都有兴趣的，但是它代表的事情是 generative model 可以做，就是你用现成的一些模型，你可以做的事情其实还蛮多的。好，所以这边给你一个可能的一个想象的一个素材。This one is quite promising, but the thing is, okay, let me first show it is retargetable like Gaussian facial Gaussian translator. So it can do the construct a very realistic face in a 3D dimensional space, which is seems to be quite useful. If you want to do a avatar or do a face, kind of like a face swap, or generate a chat bot avatar things, it seems to be possible to use it. And it actually said about the code is coming. However, we are almost like 6 months later, the code is still upcoming. So this makes it less interesting because they are not providing source. But still, there are some like data set that on the method still you can still kind of reference or see what it does. It just if you are more interested in using it, then the code is still not available. There are also some like this one is using lava and multi-field things to generate the image. in different perspective, not different viewpoint. So so again, you can see the code is upcoming, is coming soon. So it is not. It is actually quite interesting and possible model and architecture. It just there are many alternatives currently, and there is no code about it, so it makes it less interesting. But still, if you are really into this field, this is something doable. They are trying a quite plausible and reasonable approach to solve this problem. There are a lot of different ways to solve this problem, and this approach, at least they have some result to show it. And 3D generative models also, there are just too many models about it. 所以现在有太多的3D 的生成模型，然后这也是其中一种。那个时候可能还没有那么多但是生成3D 模型这件事情，现在有太多的不同的方法。那这边可以看到，其中过去它也是利用这种方式，用 Video Diffusion Model，然后可能配上一些3D 重建的方式，去想办法让它做到更高解析度。但是现在的新的开源模型，就是这东西，就是你看这边的看起来不错，对不对？但实际上你真的去跑的时候，它的结果通常都没有那么好。然后大部分的情况就是超过 data set 之外的东西的时候，就会它还重建出来，但是它的模型就是品质不会很好，会很粗糙。那从过去到现在为止的话，就是很多不同的方法去做它。那现在的东西，你看到半年前跟现在，其实现在有好几个新的模型出来，品质都算是还不错的所以这个现在的那个功能性就降低了不少。但你看到，为了要做这件事情，其实大家都有一些不同的路线去做。Okay, and this one is still quite useful, although you might not want to use it directly. How does it can be used? Because this actually provide a general idea of how to do style transform, like this one, without do the fine tuning, without do fine tuning. 好，所以这边的重点，这个东西倒是可以用但是你可能不会直接用它的结果或 demo， 而是用它的方法，因为这本来就是要用它的方法的它的那个程式码可以让你参考。So what it is can be used on any diffusion models, but when you do the inference time, you can do some modification to the diffusion model, so to control its style. So if you have a reference style here, you can actually generate using a existing diffusion model to generate it according to a reference style. And if you have some content, also you can generate the things by using this content, like right here. You have this content, and you can generate the content, generate an image with the same content. So why does it is useful? Since we already have others like the IP adapter or like control net things or T2I adapter or a lot of different like PULID, PUL ID, PULID to do kind of like the face swap. If you are interested in the reference of content, but the content is a human. So we already have a lot of tools. This one does not seem to be that. The result is not that impressive. It is okay, but not impressive. Why is this still relevant? 所以这个结果其实还好而已啊。那我们有其他方法，为什么我觉得我会说它还重要 ？The reason is it can be useful for like 3D diffusion model or video diffusion model. So because when you have a new diffusion model like 混元 or like the new one like WAN, WAN, just released, it is amazingly good. But if you want to do like other modification like control net things or like adapter things, it might be difficult because it is difficult to even for now to train or fine tuning or modify a video model, because video model is generally like 10 or like 20 times larger or even larger than, or maybe even like 50 times larger than an image model. So it is difficult to do the fine tuning or modification like image models, image generative models. So if you want to achieve something like stylization or content by composition, content style composition things, it is should be better. Although instead of using like a control net or adapter, you can actually use this the method like this one. There are several methods similar to this one without using any training. You can use this RB modulation method or other training free method to do it on the video diffusion models. Okay. There are that something like inverse like a latent method to do similar things. Okay. Also, just historical notes are reminding that OpenAI 01 preview was actually available starting from September. So now we already have 03, and recently we have like cloud coding, Grok 3, and of course we have like DeepSeek R10, R1 models already. But the 01 was in fact back then starting available from September, which is okay. I've kind of forget it until now. Okay, so that's all for today's content. So next week we are going to talk more about the creational autoencoder. 好，so 助教就请帮忙把那个作业把它上上去。And after the next week, we are going to talk about autoregressive models, which may be which will complete some certain part that we are supposed to be talk about in the next week. That is VQ, VAE, or VQ gain. 好，所以下礼拜我们会讲到 VQ, VAE, VQ gain， 但它有一部分我们不会讲到，因为那个东西会在 autoregressive model 在下礼拜的时候才会讲到。And autoregressive model is kind of the paradigm of the GPT style models. So after we talk about simple image autoregressive models like Pixel CNN, Pixel RNN, the next week we are going to talk about decoder-based large range models like GPT. 好，所以在下礼拜所以我们接下来下礼拜是 Facial Autoencoder， 再来是 Autoregressive Model， 那个绝对就是也是一个礼拜会讲完，然后再来的话就会进入语言模型的部分了。好，所以这大概是接下来3个礼拜的情况。好，那今天的话我们就上到这边。